Okay, let's start with a pretty wild question. What if the buildings around you, the concrete, the glass, the steel, what if they could fix their own cracks,
Uh-huh.
filter pollution out of the air, and maybe even eventually build themselves without anyone lifting a finger?
That's exactly what we're diving into today. This is the deep dive where we pull out the essential info on nanotechnology and self-assembling systems in construction.
Yeah.
And you're about to get the shortcut, basically, to understanding this huge transformation that's happening.
We're digging into the sources to show you exactly how building things is shifting. It's moving away from just, putting up a static object that won't last forever,
Right.
towards managing something dynamic, almost self-aware, like a living system.
It's not just about finding better materials, so that's part of it. It's about controlling matter, right down at the atomic level.
And that's what's speeding up projects like crazy and, well, changing the whole job market in construction. Forever.
So let's start with something we can all relate to, unfortunately. That constant fight against things falling apart. You know, home repairs. Think about how frustrating that is. You patch the roof, you repaint the walls because they're peeling again. Maybe that crack in the foundation after a hard winter.
Oh, tell me about it. It's never ending, isn't it? You fix one leak and boom, something else starts dripping a month later.
Exactly. So contrast that whole cycle of decay and endless maintenance
Yeah.
with, well, with the structure that's built perfectly from the get-go. Defect-free.
Okay.
And it instantly, automatically fixes any tiny bit of damage the second it happens.
That kind of molecular perfection.
Yeah.
That's the promise here, right? And that's why you really need to grasp the three big shifts happening.
Let's jump right in. Insight number one. The materials themselves are starting to heal themselves. This is like a revolution happening at the micro level, inside the actual stuff we build with.
Okay, so here's a little hook for everyone listening who loves the tech side. How can a boring slab of concrete actually be smarter than the crew who poured it?
Well, it boils down to material science, but at the nanoscale. And the big example, the one that's really moving towards being commercially viable, is self-healing concrete.
Right, we hear that term thrown around. But how does it actually work? Like, how does the concrete perform first aid on itself? What's inside it?
It's actually quite elegant, engineering-wise. Instead of just being inert stuff, the cement mix has billions of these microscopic capsules mixed in. Or sometimes it's dormant biological things, like bacteria.
Okay.
So when a tiny crack starts to form, maybe from temperature changes or the ground settling a bit, that stress breaks open these little capsules.
Okay, so that lets out the repair crew that was hiding inside.
Precisely. And what comes out is the healing agent. Often it's some kind of sophisticated polymer that expands really fast and just fills the gap. Or, and this is increasingly common, it's biomineralizing agents. Basically, bacteria that wake up when exposed to air and water in the crack, and they start producing calcium carbonate.
Which is similar to the cement itself, structurally.
Exactly. It's like the concrete grows its own scar tissue, and that scar tissue is actually strong. So the benefit isn't just looks. We're talking serious reduction in maintenance costs.
And a much longer lifespan for the building, right? Maybe double or triple what we expect now.
That's the projection. And connecting this to the bigger picture sustainability is huge. When materials last way longer and fix themselves.
You use fewer resources, less energy for repairs.
For sure. Plus, these materials are often being designed so they can be, well, reconfigured using targeted heat or chemicals at the nanoscale. So you drastically cut down construction waste. It supports that whole cradle-to-cradle idea.
That idea, endlessly reconfigurable materials, that's a pretty big leap mentally. But it's not just the concrete you pour, right? The surfaces, the coatings are getting supercharged too, nano coatings.
Oh yeah, think of it like the ultimate protective suit for a building. These coatings are incredibly thin but super durable. They protect against UV light, water, rust, pollution, even microbes. Some use titanium dioxide nanoparticles. When sunlight hits them, they actually break down pollution and dirt.
So walls that literally clean themselves. Imagine the savings just on not having to power wash buildings for decades.
Exactly.
And what about glass? I know nano-enhanced glass is a big deal for comfort and energy saving.
It absolutely is. Glass treated with specific nanostructures can be really smart about filtering light.
How so?
It can block the harmful UV and infrared radiation, the stuff that heats buildings up while still letting in the visible light we like. This means way better temperature control, less need for air conditioning,
Which saves energy.
and improves health for the people inside over the long run. That's crucial for you to think about.
Okay, but I gotta ask, what are the downsides right now? This sounds, well, expensive. And maybe complicated. Are these self-healing agents really going to last 50, 100 years inside the concrete?
That's definitely the key challenge. And it adds complexity, you're right.
Yeah.
A lot of current research is focused on the encapsulation, making sure those tiny capsules of the dormant bacteria don't just break down over time before they're needed.
Right.
And yes, the cost is higher up front currently,
Mm.
but when you factor in the life cycle cost,
Yeah.
avoiding maybe 50 years of human patching and repairs, the math actually starts to look pretty good for the nanotech approach.
That makes sense. And it sets us up perfectly for part two. We're moving from materials that passively heal themselves to, well, active self-assembly.
Yeah.
So if the materials are smart, the next question is who, or maybe what, is actually doing the building?
And now we are getting into autonomous construction. This is driven by things like modular swarms and molecular manufacturing. It's where we really see the shift from human labor driving construction to swarm intelligence managing.
Okay, this definitely feels more sci-fi. You're talking about potentially huge swarms of tiny robots, either nanoscale or maybe slightly bigger modular ones,
Yeah.
working together. How do they coordinate to build something massive, like a bridge or a skyscraper?
They basically work by assembling standardized building blocks. Engineers often call them voxels. Think of a voxel as like a really smart, programmable Lego block, maybe down at the molecular level eventually.
Okay.
So unlike, say, 3D printing that builds layer by layer, these swarms can work all over the structure at once. They arrange these voxels based on a digital blueprint, totally autonomously. It's parallel construction, but on a scale we've never seen.
That's the key difference for you, the listener, to grab onto. It's not just a bigger 3D printer. It's truly distributed assembly.
Exactly. The really complex part is the algorithm that controls the swarm. How do they share space? How do they move materials around? How do they check the work in real time? It needs incredibly sophisticated sensing.
And speaking of scale and speed,
Yeah.
this is where we get the little Easter egg detail from the research sources. Work happening at places like MIT, where these little assembler robots can actually build copies of themselves.
That's the potential game changer, right? Think about project speed. If one robot puts down 10 voxels an hour, 1,000 robots can do 10,000.
Right.
But now, what if those first 1,000 can also build, say, 100 more robots each day? You get this exponential growth curve.
Whoa.
So projects that normally take years, big infrastructure stuff, could maybe, potentially, be done in weeks or even days.
That kind of speed, that self-accelerating build, that really does challenge our whole idea of how long civil engineering takes. But you mentioned the ultimate goal isn't just these modular swarms, it's true molecular manufacturing.
Molecular construction, yeah.
Yeah.
That's the peak ambition here. It means nanobots, literally laying down molecular foundations, connecting materials atom by atom, following the blueprint with perfect precision.
Which eliminates any possibility of human error or tiny flaws in the material itself.
Right. You get perfect defect-free structures.
Understood.
And this is cool. You can create totally new architectural shapes, things that maybe fold or unfold or change their form based on programming, stuff we just can't build now.
But any building that dynamic, that can change shape.
Yeah.
It needs a nervous system, right? That's the smart dust idea.
That's where smart dust comes in, exactly. It's the literal nervous system for the building.
Okay.
These are sensors maybe only a few hundred nanometers across. Tiny. Embedded right into the materials as they're assembled.
And they're constantly sending back data.
Constantly.
Yeah.
Super localized data on stress, vibration, temperature, air quality, even who's in the room.
Yeah.
It gives the building this continuous stream of information about itself and its environment.
Allowing it to adapt and predict problems.
Yeah, enabling continuous adaptation and, importantly, predictive self-monitoring for maintenance. The building doesn't just heal itself. It knows exactly when and where it needs to before the problem gets big.
Okay, but hold on. If the whole structure is run by this invisible network of tiny sensors, what about security? How do you stop someone from hacking the smart dust in a bridge or a building?
That's a critical question. It really highlights the shift from just physical security to needing intense digital resilience. The networks controlling these things have to be incredibly secure, encrypted, redundant.
Yeah.
We're not just talking about securing a server room anymore. You'd be securing the basic data fabric of the city itself. So security experts who get distributed nanoscale networks, they're going to be as vital as structural engineers.
Okay, so we've got materials that heal, robots that build. That brings us to part 3. The huge societal changes this automation causes. If robots build the cities with molecular perfection, what happens to all the people who currently wear the hard hats?
This is probably the most critical piece for you, the listener, to think about. And it's often overlooked. Those traditional construction jobs, the routine stuff, measuring, assembling by hand, inspecting, repairing, a lot of that is going to be automated.
Right.
The sources we looked at are really clear on this. The whole nature of construction work is shifting, and probably pretty fast.
So the familiar hands-on construction worker role, it has to evolve significantly, doesn't it? It's not just saying learn to code. What kind of new jobs actually emerge here?
We're seeing a big move towards what you might call creative oversight. You'll need specialists in robotic fleet optimization, people who manage and maintain these potentially self-replicating swarms.
Okay.
You'll need digital twin managers. These are people who manage the super precise virtual models of the real buildings. These models are used to test out repairs or upgrades digitally before the autonomous systems actually do them physically.
So the job changes from physically building the wall to managing the digital plan that tells the wall how to build or repair itself. That's a huge shift in required skills.
It absolutely is. It means education has to adapt too. If
Mhm.
you're someone who likes learning new things, the learner, this is a massive opportunity. The demand for people who understand robotics, material science, complex digital systems, that's going to explode. Way more than the demand for manual labor.
And all this complexity, this interconnectedness, it feeds directly into the larger idea of the smart city, right?
Definitely. If every single building is self-monitoring, self-healing, adaptive, basically a dynamic system, then the whole city becomes truly aware, in a
How
sense.
so?
Integrating nanotech throughout urban infrastructure allows for real-time optimization in ways we can't do now. Think about traffic jams, say, in Mumbai or LA. Instead of static traffic lights, you could have infrastructure that actively senses congestion, building up, and reroutes resources, energy, water, maybe even autonomous vehicles minute by minute, based on that molecular level monitoring.
And for you, the individual living in that city, it means a big upgrade in safety and resilience day to day.
Absolutely. The structures themselves become actively protective. Buildings that automatically heal tiny damages can withstand extreme weather much better without needing emergency crews. They can adapt to environmental shifts. They can actively protect people inside from pollution or even airborne pathogens using advanced nanofilters built right into the walls or ventilation. It's a huge leap forward for public health and just basic civil resilience.
So the key takeaway here, really the core idea of this whole deep dive, is that the very concept of a building is changing. It's shifting from being a static object
Right.
to being a dynamic, programmable, almost living system.
And that transition needs people. People who can manage the programming, oversee the systems, and guide the evolution of these structures over time.
Okay, let's quickly recap the three huge revolutions we've touched on today. First, the materials themselves are getting smarter. Self-healing concrete using things like biomineralization, nano-enhanced glass.
Yep. Second, the way we build is changing. Autonomous robots working in swarms, assembling structures from voxels, maybe even replicating themselves to speed things up dramatically.
And third, the massive societal shift that comes with this, leading to genuinely aware smart cities, but also requiring a big change in the workforce towards roles like digital twin managers and robotic fleet specialists, fundamentally altering global labor needs.
Yeah.
Which brings us to our final thought, something for you to chew on after this. We talked about structures that can heal themselves, monitor themselves, upgrade themselves, maybe even change shape. If the maintenance is constant and automatic, happening inside the material itself, if the actual form of the structure is programmable, fluid, is it still just a building? Or is it more like an enormous programmable machine that's designed to evolve?
It's a big question. This isn't just about building things better. It might be about moving beyond static structures altogether.
Yeah.
If you know anyone working in architecture, engineering, urban planning, maybe share this deep dive with them.
Yeah, understanding this shift now is really key to navigating the next few decades of how our cities work and feel. And remember, every insight gets deeper on the second listen, so make sure you save this episode in your library.
And next time, we're going to follow this thread of molecular level change.
We'll unpack the sources showing how nanotech could lead to personalized items made on demand, maybe just by pushing a button, and why the whole idea of a big centralized factory might actually start to disappear.
You really won't want to miss how these systems could totally reshape global supply chains.
We'll see you then.